Hello, my name is Piotr Sliwa, and I would like to present my work on community detection analysis in multi-layer COVID-19 patient similarity networks. This was supervised by Heather Harrington, Gesine Reinert, and Julian Knight, and was made possible thanks to the efforts of the COMPAT consortium. Within the consortium, data on 115 plus COVID-19 patients was collected, as well as severe flu patients, non-COVID-19 sepsis, convalescent, and healthy volunteers. From these patients, then blood was collected, and a number of different biological assays were performed on that, including single cell and bulk transcriptomics, proteomics, cell composition measurements, and others, as well as these patients were clinically characterized. So the data set looks like that for each of the patients, and we have a number of patients spanning different severities of the disease. We have a number of columns. These columns represent different modalities, and these columns have different lengths because they have different numbers of features. Some patients don't have all the modalities, but a large group of them has a sufficiently large number of modalities. We then take each modality at a time and construct separately similarity networks, so patient-patient, or to be more precise, sample-sample similarity networks. So we first pre-process the data, then we calculate similarity and threshold it at some value, and we get this network, for example, for like timsTOF, and we get other networks for other modalities. And the first question is how to create networks that are consistent and informative. We use CoGENT method developed in Gesine's group. We divide the data into two sub-data sets, which have an overlapping part of features and a unique part of features. We then choose specific network construction methods, so the specific way of preprocessing the data, and then a specific type of similarity measure along with thresholding parameters and so on. And we get these two networks. They should be similar because the sub-data sets share a large chunk of information, and we can measure that similarity. We can do that a number of times and assess how consistent that network construction method is. And we can then, by basically resampling these different sub-data sets, and we can scan in this way across different methods and parameters to determine the optimal choice in terms of consistency. What we get is, for example, this is one of the pre-processing approaches, so the dimensionality reduction approach, where we only take top variable number of genes or features at a time and construct the networks using them, and then on the y-axis you have the sparsity parameter, so how you want to determine your threshold, and so how sparse you want your network to be. And we basically get different values of CoGENT score, and the most consistent parameter choice is marked by the cross here. And then we can also, on the left and right, assess how sensitive to slight changes it is. So this is when you slide across rows and across columns, you get the plots on the left and right showing you the CoGENT scores across these different values. And we then choose the optimal choice and construct network. This is an example of the Luminex network. Rows and columns are ordered according to clinical state, so healthy volunteers, convalescent patients, non-hospitalized COVID patients, different manifestations of hospitalized patients, and sepsis patients. On the right, we also have some data on some of the clinical covariates. And whenever there's a dot, that means that the two samples were sufficiently similar. So we do that for all the different modalities that we assess. We see that the different modalities show us different information on these patients, and we connect that into a multi-layer patient similarity network, and we run community detection on that. We see that the detected communities, which are shown on the right, closely correspond to what the doctors have determined. So whether the patients were non-hospitalized, whether they had COVID, or whether they had sepsis. So we are able to discover that in an unsupervised way based on the molecular information that we have on these patients. And then we show that multi-layer approach is better than looking at single layers on their own, and there are multiple reasons for that. One of them is that we are able to classify more patients, so always using multi-layer networks allows us to classify the most patients in comparison to any of the single-layer approaches, just because some of the modalities have missing data. The additional patients that we are able to classify are classified with high score, and we assess that using normalized mutual information and adjusted front index, comparing against the ground truth that the doctors have determined. And also the nodes that were already classifiable within a single modality, they mostly improve the quality when we use multi-layer networks. In one case, the quality decreases, and in one it stays the same. And then we move on from detecting communities to understanding what is driving this molecularly. So we look at molecular pathways from KEK and reactome, and we calculate sample-specific pathway scores. So we rank, transform the expression values, and get the average rank of expression levels of genes within a given pathway. And we and then compare that and calculate that for drug-related and immune system-related pathways. So on the left, you see that the detected communities have distinct activities of drug-related pathways. This is response to corticosteroids. Then the middle one is JAK-STAT signaling pathway, and hallmark coagulation is at the bottom. And then on the right, we see that these patients also have distinct immune system related pathway activities, especially here in the coagulation related part at the bottom. So in summary, we've integrated information from a multimodal health data set. The communities that we discovered through our unsupervised approach, they correspond to major clinical states. Our method performs better than single layer networks in the ways that we've described, and discovered communities have distinct activities of drug-related and immune system-related pathways. Thank you very much for your attention, and thanks again to Gesine, Julian, and Heather, and the Combat Consortium.